What do you know about dark matter? What is it? Why is this topic one of the most discussed in modern science? Why is the number of studies on this topic growing from year to year? Why do scientists look for alternative hypotheses to explain the observed facts? What is all this for? Probably there are some observations that are not explained by the hypothesis of dark matter. What are these observations? Let's try to find out. In this video, I will not criticize the dark matter hypothesis. There is a lot of content on the web about this topic. Now I will try to answer questions that do not find answers in existing theories and hypotheses. Perhaps the most important argument in favor of the existence of dark matter is the inexplicable movement of stars in galaxies. Flat rotation curves of galaxies indirectly indicate the presence of a huge amount of invisible gravitating matter within and even far beyond the visible part of the galaxy. And the visible amount of matter is too small to provide sufficient gravitational force to keep stars with such high speeds in their orbits. But the rotation curves of galaxies are not the only strange thing about the behavior of stars and galaxies. There are other unexplained phenomena, about which the general public knows very little. Let me remind you that the main elements of these galaxies are the disk, the bulge, and the stellar halo surrounding the disk. The main difference between these main elements is that in the disk the stars move in one direction and in orbits close to circular, while in the halo stars do not have an ordered movement, and their orbits, to a great extent, have elongated shape. In addition, the movement of stars in these structures also differs in speed. So, for example, the speed of stars in the disk of our galaxy, in the area where the Sun is located, several times higher than the tangential velocity of halo stars. And here it's necessary to make an important remark. The fact is that the speed of halo stars can be divided on two components, on a tangential component and radial component. The radial component is due to the transition of the potential energy of the gravitational interaction into kinetic energy of the gravitational interaction and back, just like how the speed of pendulum changes. And the tangential component depends on the force of gravity in the place where the star is moving. An exactly tangential component is used to study the gravitational potential. And it's precisely the tangential velocity of the halo stars is several times less than the tangential velocity of the disk stars. And if we look at how the gravitational force acting on disk stars and halo stars is determined, then we will find that stars with the same orbital radius should be affected by approximately the same forces. And accordingly, these stars should have approximately equal tangential velocity. This equality of forces comes from the equality of the virial mass contained in the spheroids of their orbits. In addition, here it's necessary to take into account the fact that based on the virial mass formula, if the speed of bodies in the case of orbits of equal size, for example, differs by a factor of 2, then the mass contained within the orbit differs not by a factor of 2, but by a factor of 4. And if the speeds of bodies differ by a factor of 3, then the mass by 9 times. And as we can see, the speeds of stars in these subsystems are very different. And on this basis, two assumptions can be made. Gravity of dark and ordinary matter acts selectively. Gravity acts strongly on disk stars, but weakly on halo stars. And here it's necessary to mention the interesting fact that the stars of the halo and the disk also differ in age. In our galaxy, halo stars are oldest, at 13–14 billion years old, and the disk stars have different ages, from a few years to about 8 billion years. That is, it's possible that the strength of gravity depends on the age of the star. And such a formulation of the question is not without meaning, and a little later you will understand why. Or the reason is completely different, and the force of gravity depends on the subsystem in which the star moves and what orbit it has. Another very strange phenomenon is that in the disk of our galaxy and other galaxies, stars can move at different speeds. In astronomy, this phenomenon is called asymmetrical drift. In part, this is due to the fact that the stars, in addition to the circular motion around the center of the galaxy, can have an oscillating motion related to the plane of the disk. This happens when the disk stars, due to the interactions between themselves and the halo stars, but mostly due to the mergers with satellite galaxies, increase the randomness of their movement. This process is called disk warming, but the spread of velocities in the disk is too large to be explained by the presence of a large vertical or radial component. The stars in the disk do not have high vertical or radial velocities. And if the stars have a high vertical velocities, then they will leave the disk, and the galaxy will lose thin disk structure. But whatever the cause of this phenomenon, in the classical sense of orbital motion, two forces act on a star in a galaxy: the gravitational force and the centrifugal force. And the centrifugal force depends on the speed of the star, moreover quadratically. And there must be a balance of forces, because if the speed is too high, then the star flies away from the galaxy. And if it's too small, then it goes into orbit closer to the center of the galaxy. And based on the classical understanding of orbital motion, there should not be bodies in the same orbit with very different velocities. This means that there must be some rational explanation for the fact that in galaxies in the same orbits, stars move at different speeds. Adding to the intrigue is a relatively recent study of asymmetrical drift in the nearby disk galaxy Andromeda. The researchers found that this phenomenon has an age dependence. That is, the speed of stars depends on age, and in the Andromeda galaxy, the youngest stars move the fastest. Gas clouds move a little slower. And then the speed gradually decreases with increasing age of the stars. And the oldest stars of the disk have the lowest speed. But it's about average speed, because there are very fast old stars and very slow young stars in the disk. The authors of the article argue that this effect cannot be caused by the fact that halo stars were mistakenly included in the sample of stars, because the selection of stars was quite careful. And even if halo stars somehow got into the sample, this could not affect the result for other ages. The authors of the study also suggest that such a heating of the disk could be the result of many regular mergers with small galaxies, which should have been distributed evenly over time throughout the evolution of this galaxy. But this is only a possible cause for the appearance of the velocity scatter. And this doesn't explain how stars in the same orbit can have such different speeds and still retain a thin disk structure. For a better understanding of the problem, I will give a very good example. In the Andromeda galaxy, the scatter of rotational velocities is so high that the maximum and minimum velocities in the disk differ by more than factor of 2, which of course cannot be explained by the presence of a high vertical speed. Otherwise, these stars would no longer belong to the disk subsystem, and they would go to the spherical subsystem. What the authors of one of the works are actually talking about. The explanation of this phenomenon is complicated by the mysterious connection between the speed of stars and their age. As if gravity acts on old stars more weakly than on young stars. Or maybe there is an explanation for this phenomenon, simpler but not so obvious, in the framework of the classical understanding of gravity. In general, it must be said that the existence of thin, gravitationally stable disk galaxies with high speeds has become a real challenge for modern science. And even now, to the structure and evolution of galaxies, there are a lot of questions that are still unanswered. And no doubt that any theory that claims to be a working theory must explain all these oddities. And it's possible that you and many others have not yet heard about these oddities, precisely because they are not explained by the dark matter hypothesis, which explains rotation curves and thin disk well enough. And if we take into account everything known to date, it may seem that a completely different physics works on the scale of the galaxy. And in the next part of the video, I will try to define this physics. What exactly is dark matter? If we look at how the stars move in the galaxy, then we will see not just a slight deviation from the predicted speeds, but we will see a completely different character of the dependence of the speed of stars on distance. And such a distribution of velocities of stars can be explained if we imagine that these galaxies are not a cluster of matter in the form of a disk with a consolidation in the center, but the accumulation of matter that is distributed in the galaxy and even far beyond of the disk of the galaxy. A kind of spherical accumulation of matter, which in size exceeds the apparent size of the galaxy. Moreover, the total mass of this matter sometimes exceeds the visible mass of the galaxy by orders of magnitude. In other words, dark matter is a halo of invisible matter about a spherical shape that permeates the entire galaxy and extends far beyond it. Over the years of research, scientists have discovered several patterns which lift the veil of the mystery of this phenomenon. A connection was found between the speed of rotation of a galaxy and its luminosity, the dependence of Tully-Fisher. The brighter the galaxy glows, the faster it rotates. Obviously, that the luminosity of a galaxy is related to the amount of baryonic matter. That is, that the more luminous matter in the galaxy, the faster it rotates. This dependence has a fairly high accuracy, and it can even be used as a method for determining distance from the luminosity and rotational speed of a galaxy. All types of galaxies fit well into this dependence, except for some types of dwarf galaxies and some types of galaxies with low surface brightness. It was also found that the form of the rotation curve depends on the morphology of the galaxy. That is, different types of galaxies have a preferred type of rotation curve. Studies have revealed how the rotation curve depends on the morphology type and on stage of galaxy evolution within this type. For example, very often in elliptical galaxies, the rotation curve falls off rapidly, which indicates that the content of dark matter within the visible part of elliptical galaxies is rather small. Also, in the process of studying of rotation curves, the researchers came to the conclusion that the zone of dominance of luminous matter smoothly passes into zone of dominance of dark matter, and this doesn't affect the rotation curve, which is most often flat. But in the process of collapse of ordinary matter in the dark matter halo, the mutual distribution of these types of matter can have a different combination, which should be expressed in different types of rotation curve. But instead, there is such mutual distribution that gives a flat rotation curve. Therefore, there's a problem of explaining this phenomenon, which sounds like a conspiracy of dark and baryonic matter, or the problem of fine-tuning the parameters of the galaxy. But this situation is true not for all types of galaxies. There are systematic deviations that violate this conspiracy of dark and luminous matter. For example, bright massive galaxies tend to have their rotation curve slope downwards, while the rotation curve of low luminous dwarf galaxies tends to grow at all distances from the center. And this fits perfectly into the concept of dark matter, because massive bright galaxies have a lot of luminous matter within the visible disk, and the relative contribution of dark matter is correspondingly low. And in dwarf galaxies, the relative density of ordinary matter is low, and therefore the contribution of dark matter to the total gravity grows very strongly with the distance from the center. And these features of the rotation curves are indirect confirmation of the existence of dark matter. Based on the dependence of the rotation curve on the luminosity of the galaxy, a mathematical model of the universal rotation curve was created, which, with a given parameter of the luminosity of the galaxy, predicts the shape of the rotation curve with good accuracy. A strong correlation was found between the distribution of ordinary matter and the rotation curve, and this prompted to the idea that ordinary matter dominates in interaction with dark matter, and dark matter adjusts to the distribution of ordinary matter. And this has found its expression in the baryonic scaling model, with the help of which, from the density distribution profile, it's possible to obtain a rotation curve. That is, in other words, it all seemed to hint that even if dark matter exists, it manifests itself very reluctantly, and everywhere willingly obeys the luminous matter. And instead of showing its heterogeneity in the form of cusps, that is, in the form of a high density of dark matter in the center of the galaxy, which are the result of dark matter simulations. On the contrary, in some cases, calculations show a decrease in the density of dark matter in the center of the galaxy. In general, observations suggest that dark matter is a very strange phenomenon. And before the study of movement of stars in galaxies, before the study of movement of galaxies in clusters, there was no need for dark matter. And all our observations within the solar system were consistent with theoretical calculations. In the solar system, the motion of planets is determined by a regularity that relates the speed of a planet to the mass of matter contained within its orbit, more precisely inside the spheroid or ellipsoid described by this orbit. And knowing the speed of the body and the parameters of the orbit, it's possible to determine the mass inside the described orbit. This mass is called the virial mass or dynamic mass. But what the reason do we have to believe that this relationship of mass and velocity works properly on a galaxy scale? Can we scale the known laws of physics that work in the solar system to the scale of the galaxy? Are there fundamental differences between the solar system and the galaxy? And from the standpoint of the traditional understanding of gravity, there are no fundamental differences between the galaxy and the solar system. Yes, matter is distributed in different ways, but this should only be reflected in the different pattern of decrease in the speed of objects in this system. There is also a difference in the order of magnitude of the mass of matter. The mass of the galaxy is billion times greater than the mass of the solar system. And in the classical theory of gravity, the force of gravity depends linearly on the mass, and can be scaled to the size and the mass of the galaxy without change. These are main differences, but there is one fundamental difference, which is visible only from point of view of theory of moving space. In short, I will tell a little about the theory for those who have not seen the previous videos. In the theory of moving space, space moves from all sides into every particle of matter, and the space is accelerated due to the narrowing of the flow, like the flow of perfect fluid. This acceleration of space creates a force of inertia, which manifests itself as a gravity. And it's the movement of space, in contrast to the stationary, gives a basis for the equivalence of an accelerating reference frame, and reference frame at rest in a gravitational field. Gives a basis for the equivalence of inertial and gravitational masses, the equivalence of gravitation and inertia. The space of the universe is expanding, and therefore photons flying in space are expanding, which creates the effect of cosmological redshift. This expansion of the space of the universe, together with the inertial coupling of space and matter, acts upon the matter like a kind of quasi-pressure and causes the matter of the universe to fly apart. The rate of expansion of a unit volume of space is constant. Therefore, the density of dark matter which is responsible for the expansion of the universe, doesn't change with time, and doesn't depend on the total volume of the universe. And since the expansion rate is constant, but the volume of space in the universe is constantly increasing, the universe is expanding with acceleration. This movement of space into every particle of matter manifests itself as a fundamental connection of elementary particles with space that is responsible for the presence of mass. And the space in particles doesn't accumulate, but is converted and is responsible for the presence of an electric charge. This and many other things are described in more details in previous videos, or will be described in next videos. Explanation of the movement of the bodies from the standpoint of the theory of moving space is fraught with difficulties, which are related with the fact that many phenomena, concepts and effects have to be described for the first time, relying on logic and intuition. Therefore, errors are very likely. Unfortunately, in modern physics, there's no section with title like "The movement of bodies in a moving space changing direction." And the expression "movement of space" is a bit confusing, because the movement of the bodies in physics is considered relative to the other bodies or space. But I ask you to focus and try to understand the ideas that I want to convey to you. But before we begin, it's necessary to mention that the force of inertia is not a real force, but a fictitious force. And this is due to the fact that the behavior of this force differs from the behavior of real forces. For example, when a body orbits under the action of gravitational force, then the force of inertia, that is centrifugal force that acts on the body, is equal in absolute value to the gravitational force and is oppositely directed. In this case, the sum of the forces is zero and the body should move straight, but instead the body moves in orbit. Or another example. When a force is applied to a body, an inertial force appears, which is equal in absolute value to the applied force, but opposite in direction. And here also, the sum of the forces is zero, and the body should remain in place, but instead the body moves with acceleration. Therefore, often, the force of inertia and its manifestations are called fictitious, imaginary, or pseudo-force. But in all its manifestations, the force of inertia counteracts the change in the speed of the body relative to space. And due to the fact that the gravity is considered as manifestation of inertia, then gravity and the behavior of matter and space must be considered inseparably from the movement of space and only in the context of movement of space. Therefore, I want to warn you that further thoughts will sound that at first glance may seem counterintuitive, but logical if we consider inertia and gravity as a manifestation of the connection between matter and space. The speed of space in a galaxy depends on the distribution of matter. It's not difficult to see that with increase in the amount of matter in a flat disk, the component of velocity of space lying in the plane of the disk increases very much. Let's focus exactly on this component. Let's consider the three simplest cases when the matter in the disk is distributed without sharp changes. And depending on the distribution of matter, the speed of space in the process of moving from the edge of the galaxy to the center may decrease, increase, or remain constant, because in the process of moving of space, there are two parallel processes that affect its speed. Due to the narrowing of the flow, space is accelerating, and due to the fact that space is absorbed by matter as it moves, it slows down. Due to the fact that the narrowing of the flow of space depends on the morphological type of the galaxy, as well as on the structural part of the galaxy, in which the movement occurs. This narrowing can be very different for each galaxy. Let's call the function of narrowing of the flow of space the alpha function of the galaxy. In order for the speed of space to remain constant in the process of moving towards the center of the galaxy, it's necessary that this alpha function coincides with the mass distribution function in the disk. Let's call the mass distance distribution function the beta function of galaxy. And if these functions do not match, then the speed of space either increases or decreases. And now if we compare the galaxy with the solar system, then in the case of the solar system, the speed of space towards the Sun, firstly, is very small, secondly, it's isotropic, and thirdly, space in the entire solar system is moving with acceleration towards the Sun. And therefore, the force of gravity in the solar system is isotropic and has a clear dependence on distance. But in the case of the galaxy, the velocity of space to the center of the galaxy, firstly, is higher by orders of magnitude. Secondly, in these galaxies there is a strong pronounced anisotropy of the velocity of space. And thirdly, space in the disk of galaxy can speed up, slow down, and remain unchanged, what depends on the ratio of alpha and beta functions. And these differences in the movement of space radically change the situation, change the physics of movement in the galaxy. First, if we take into account the speed of stars and the speed of space, it turns out that in fact the stars do not move in closed orbits, but as it were, they fly apart from the center of the galaxy along spiral trajectories. But the movement of space towards the center of the galaxy compensates for this expansion and stars remain in their orbits. And secondly, the movement of space in the disk of the galaxy is always directed towards the center of the galaxy, and in different parts of the orbit it has a different direction, but always to the center of the galaxy. Therefore, while moving along the orbit, the stars experience a constant change of the direction of space. That is, rectilinear motion by inertia here will no longer be rectilinear, because every particle of matter is inertially connected with space, and any manifestation of inertia occurs only when, due to the external influence, the velocity of the body changes relative to space. And the appearance of centrifugal force occurs only in the case of deviation of the body from motion by inertia. But in the case when the star is moving in orbit and space is moving towards the center of the galaxy, then for the star, the trajectory of motion by inertia will no longer be a straight line. The trajectory will depend on the ratio of the speed of space and the speed of star, and the greater the velocity of space relative to the orbital velocity, the more the body inertially depends on the direction of motion of space. That is, it turns out that if a star moves in space that changes its direction, then it changes its direction together with the space. This effect can be imagined as the force of inertia, which preserves the direction of movement of the body relative to the direction of movement of space. But since the direction of movement of space changes, then direction of the star is also changed. Or it can be imagined as the action of a virtual force of the same nature as all kinds of manifestations of inertia. The force that neutralizes the centrifugal force. The force that makes a star move around the center of the galaxy as if it were moving in a straight line by inertia. I call this force the reactional force of space. Now I will try to formulate the basic rules for the movement of stars in the galaxy in different modes of movement of space. If the main condition for the emergence of the gravitational force is the acceleration of space, then, in the case when the space moving from the edge of the disk to the center of galaxy doesn't change its speed, then gravity doesn't work. Also, on the bodies whose speed is less than the speed of space, centrifugal force is not working. And all the bodies moving around the center of the galaxy, in this case, move freely by inertia. Centrifugal force begins to act on the bodies that have a speed greater than the speed of space. And look how interesting situation turns out. If the bodies move around the center of the galaxy as if by inertia, then when you try to change the direction of movement of such bodies, In such case, an inertial force will appear, that is the reactional force. It turns out that the bodies moving around the center of the galaxy, having a speed below the speed of space, are in a kind of inertial trap that can only be overcome by overcoming the reactional force of space. And this force depends on the difference between the speed of the body and the speed of space. When space moves towards the center of the galaxy with acceleration, the force of inertia appears, which forces the body to move so that the space around the body doesn't accelerate. That is, the body begins to accelerate as well as space. This is the effect of the force of gravity. But in this case too, bodies also move in inertial trap, and the force of gravity is counteracted by the reactional force, and due to the presence of gravitational force, the bodies in orbit have a maximum speed more than speed of space. If space is slowing down, then, based on the reverse logic, the force of inertia must acting in the opposite direction of gravity, the counter-gravity force, if I may say so. This force is also counteracted by the reactional force of space. Because of this force, the maximum orbital speed must be less than the speed of space. As a result, we have a relationship between the speed of space and the maximum speed of the orbital motion of bodies. It turns out that stars in the galaxy are moving in inertial trap, created by the movement of space. Therefore, there are such high velocities of stars and such abnormal distribution of velocities of stars in the galaxy. And the gravitational attraction in massive galaxies fades into background, and the leading role in keeping the stars in the galaxy is played by inertial trap. And based on all that has been said, we can conclude the following. It's impossible to determine the mass enclosed inside the orbit of a star by the speed of this star. That is, the value of the virial mass gives overestimated value. Since the speed of the stars in the inertial trap is obviously higher than the speed which would be due only to gravity. And this is the main reason for the appearance of invisible mass in the analysis of the stellar rotation curves. Exactly this discrepancy gave the main basis for the appearance of the dark matter hypothesis. Reactional force or inertial trap effect acts in case of any movement that occurs across the movement of space, and it doesn't work only in the case of movement parallel to the direction of movement of space. And as can be seen from the distribution of velocity of space, in the disk the speed of space is maximum, and the speed of space from other directions is much less, and accordingly the effect of inertial trap is stronger in the disk. Therefore, the maximum available speed of the stars in the disk is higher. And this is the reason why the speed of the stars in the halo is much lower than the speed of the stars in the disk. Another interesting effect is that in the inertial trap there is upper speed limit, which is due to the presence of centrifugal force. But at the same time, there is no lower speed limit. That is, bodies with speeds below the maximum can be in the same orbit with faster, and do not fall towards the center of the galaxy. And this explains why in our galaxy and in other disk galaxies we observe an asymmetrical drift. But the relationship between the amount of the drift and the age of the stars is a consequence of the evolution of the galactic disk, the consequence of how the speed of space in the disk changed. I will talk about this in the next video. Also, if you look closely, you can understand how such drops are formed in the rotational curve. There are several other effects that affect the dynamics of stars. For example, how does this type of rotation curve form for massive disk galaxies? Or why, in the vicinity of black hole, stars behave very close to what the classical theory predicts? I will also talk about this in the next video. But there is another very interesting effect. There is a very deep potential well near the galactic nucleus, and if the body has sufficient speed, then it overcomes this stage of the potential well. If this is followed by a zone with a constant velocity of space, then in this zone the body freely moves further by inertia, as if slipping further along the disk, until it reaches a zone where space accelerates or slows down. If space accelerates, then gravity begins to act in this zone, and in this zone the body will stop if its speed is not enough to overcome the emerging gravitational force. But it's also necessary to take into account that the body enters the zone with a low speed of space, and according to the law of inertia, should increase the radial velocity. If, after a zone with a constant velocity of space, there follows a zone with space deceleration, then the body will also stop with a high probability, because the speed of space begins to grow there. That is, the second stage of the potential well begins there. So, we see that the potential well in the disk of the galaxy has a step in the form of a zone with a constant velocity of space, having climbed on which the body moves freely to the end of this zone. In turn, further accumulation of matter at the edge of this flat zone changes the speed of space in the subsequent zone. Therefore, there is a constant displacement of the space acceleration zone away from the center of the galaxy, and the space deceleration zone is shifting to the center of the galaxy. This is the basic physical principle of the formation of such distribution of matter in the disk of the galaxy, due to which flat rotation curves are created, and regardless of the type of galaxy. And here, no fine-tuning of the parameters of the galaxy or a conspiracy of dark and baryonic matter is needed. This is how physics of galactic disk in the theory of moving space works and creates flat rotation curves on different types of galaxies. But the scenario described above is synthetic. In fact, the process of forming a flat rotation curve is even simpler, and there are many details in this process that need clarification. But such a scenario of creating a disk with a flat rotation curve works in the case when matter comes from the center of galaxy, to which of course there is a large amount of evidence, but there is no generally accepted working theory that would explain such a scenario for the evolution of galaxies. But the theory of moving space allows and describes such a scenario. And this scenario also helps to solve many cosmological problems. And recent studies just confirm that the growth of the disk of our galaxy was carried out from the center outwards. An isotropic space velocity distribution in a disk galaxy should affect the motion of halo stars. Halo stars crossing the disk plane should change their velocity vector, due to the fact that the speed of space in disk is higher, and inertia always strives to maintain the speed of the body relative to space. The halo star will be carried away by the flow of space in the disk. After exiting the disk, the direction of movement should return to its previous value. But taking into account the fact that during this time there will be a change in the direction of movement associated with other factors. And if it's so, then surely such changes in the speed of halo stars can be detected using the Gaia telescope. In this context, interesting observations have been made. Using the data of modern telescopes, statistical studies were carried out on the distribution of the velocities of the stars in the halo of our galaxy. In our galaxy, the halo stars have a very pronounced anisotropy. That is, halo stars have very high radial velocities. It's important to emphasize here that we are not talking about high radial velocity component of halo stars, but about the fact that some of the halo stars have a clear direction directly from the center of the galaxy and back, and stars with this direction have a relatively high speed, and stars with other direction do not have such a high speed. And such a high degree of anisotropy is very difficult to explain, because it's very difficult to describe the scenario that led to this, and any proposed scenario will be artificial, unnatural, man-made. To say that the scientists were very surprised is like saying nothing, because the exclamation mark in scientific works is an extremely rare occurrence. But we know what can act as a filter to create such anisotropy. Recall that the effect of the inertial trap doesn't work only in the case of movement parallel to the movement of space. Stars having any other direction under the action of inertial trap change the direction of their movement. And note that the maximum velocity value in this anisotropy structure is roughly equal to the estimated velocity of space in the disk. But what is the mechanism for the appearance of this anisotropy? I assume that the disk stars, due to the heating, leave the disk and acquire a radial velocity, due to the fact that the stars enter the region with a low speed of space, while the inertia acts in the direction of maintaining the speed of the stars relative to space. And the effect of the inertial trap acts as a filter and filters out all stars whose direction is not parallel to the movement of space, and only the stars directed along the motion of space remain. And the filtered stars become halo stars with their typical velocities. And at the same time, the thickness of the disk remains on the verge of the maximum allowable. Of course, any explanation, even the most logical and beautiful, doesn't make sense without evidence. And there is evidence. In a relative recent study, the kinematics of the stars of our galaxy in the region closest to us was studied. And this image shows the orbital speed of the stars. The similarity with the velocity field of space is obvious. There is a tendency for the speed of stars to decrease with the distance from the plane of the disk, and the thinning of the profile towards the center of the galaxy. That is, the velocity profile of stars in the disk indirectly confirms this type of space velocity profile in the galaxy. And of course, there must be a connection between the distribution of matter in the disk and the shape of the rotation curve, because the velocity of space depends on the distribution of matter, and the rotation curve depends on the velocity of space. The speed of space decreases as it moves toward the center of the galaxy if the density of matter increases very rapidly. And on the contrary, the speed of space increases if the density of matter increases slowly. That is, there's some kind of mutual feedback between the density of matter and the speed of space, and accordingly, the rotation curve. And the researchers have been groping for this connection for decades. They created various models to explain this relationship, but the missing link in their models has always been dark matter. And in recent works, researchers just come to the conclusion that the rotation curve depends on the distribution of luminous matter, and that if the rotation curve of dwarf galaxies, which grows at all distances from the center, is scaled in units of radius, then it coincides with the rotation curve of the inner part of larger disk galaxies. That is, in other words, a dwarf galaxy is like a stretched core of a larger galaxy. But the most important observation, confirming the connection between the rotation curve and the distribution of matter, was made decades ago by the pioneers of study of dark matter and the rotation of galaxies. They found that although the distribution of matter in galaxies has an exponential form, It differs from case to case. They divided the distribution of matter in the galaxy into three main types, which are most often found, and found a relationship with the rotation curve. And more recent research has confirmed this correlation. But this correlation is not so clear, because it doesn't take into account that different types of galaxies have different ratios of sizes and masses of disk and bulge, and accordingly, the function of narrowing of flow of space, that is, the alpha function, is different, and here it acts as a known variable, and so the correlation is not so clear, because the galaxies with same beta function can have a different alpha function. But even without taking into account the alpha function, this fundamental relationship can be traced, which was done in one of the latest works, where an inverse mathematical model was created, with the help of which, from the data of the rotation curve, one can obtain the distribution of matter in the galaxy, that is, the beta function. The result of the work, averaged over all the studied galaxies, including elliptical, fit perfectly into the theory of moving space. And here also, the authors came to the conclusion that there's no need for the presence of dark matter, and the kinematics of galaxies can be described by ordinary matter. The problem lies only in the absence of the necessary theoretical basis, or in the fallacy of the existing one. In the same work, it was noted that the distribution of matter depends on the morphological type of the galaxy, and this is also an indirect confirmation of the theory. Also, I found one paper investigating the dependence of the slope of the rotation curve on the distribution of surface brightness. But it should take into account that the distribution of surface brightness doesn't give complete information about the distribution of matter in the disk, because matter in the form of dust and gas is not taken into account. But even in this situation, there is a clear correlation. I scaled the brightness profiles and rotation curves of 37 galaxies from this work to a single scale, and you can see for yourself that galaxies with ascending rotation curves have a different distribution of matter. But what do we see in our galaxy? How is matter distributed in our galaxy? Our galaxy has a fairly large bulge, and the rotation curve can conditionally be called flat. And for the rotation curve to be flat, the beta function must match the alpha function. For a globular accumulation of matter, the alpha function is inversely quadratic to the distance. For a flat accumulation of matter, the alpha function is inversely proportional to the distance. And for our galaxy, the alpha function should be somewhere between these values. I didn't find data of the distribution of matter in the disk of our galaxy on the flat part of the rotation curve. But many years ago was measured how matter distributed from the center of the galaxy, including galaxy core. And this distribution fits the expected range well. But don't forget that our galaxy has a pronounced bulge. In addition, the measured distribution of matter also affects the core of the galaxy, where the rotation curve is not flat. So, the distribution of matter in our galaxy fits the theory well. This relationship between alpha function, beta function, and the rotation curve is the reason for the relationship between rotation curve and morphological type of the galaxy, because the morphology of the galaxy essentially determines the alpha function, and here the beta function acts as a known variable, without taking into account which you cannot get a clear correlation. And if ordinary elliptical galaxies with low ellipticity have an alpha function which is close to inverse square at all distances, it's obvious that its rotation curve will have a downward slope. In this regard, it becomes obvious that the Tully-Fisher dependence is a consequence of the fact that the more matter in the galaxy, the more space is involved in the process, and the more space, the higher its speed. The higher the speed of space, the higher the maximum rotation speed of the bodies. But at the same time, galaxies in their evolution tend to such a type of matter distribution, which gives a flat rotation curves. And the result is, the more massive the galaxy, the faster it rotates. The connection between the speed of space and the speed of the movement of stars solves the most important problem of explaining the problem of speeds of stars in galaxies, especially in the case of dwarf galaxies, in which the growth or the rotation curve continues even beyond the boundary of the visible disk. And the speed of the gas at the edges of these galaxies indicates to us the presence of invisible matter, which has a mass hundreds of times greater than the visible mass of the galaxy. But if we look at this situation from the standpoint of the theory of moving space, then we don't need any invisible matter, only the movement of space is needed. Often, as a proof of existence of dark matter, cited as an example of a galaxies without dark matter, or galaxies almost entirely composed of dark matter. But most of these galaxies, in which there is very little dark matter, belong to the class of ultra-diffused galaxies, and one of which has a mass of orders of magnitude less than our galaxy, and at the same time, its size is comparable to our galaxy. And accordingly, the speed of space there is also orders of magnitude less than in ours. And if the speed of space is less, then the effect of inertial trap is weaker, and accordingly, the effect of dark matter is orders of magnitude smaller. Therefore, the movement of stars is very close to what the classical theory predicts. But someone might argue that there are other ultra-diffused galaxies in which dark matter has been found in normal amounts. But the fact is that the name of the type of ultra-diffused galaxies only speaks of their high diffusion. But does this classification have clear limits on the density of matter? I don't know. You can see the first impression of the astronomer who studied it. And based on his impression, I doubt that this ordinary galaxy in its class, and that hundreds of such galaxies have already been discovered. But in recent years, thanks to the use of new telescopes, astronomers have begun to detect such galaxies without dark matter more often. And a recent study suggests that galaxies that have little dark matter are very large in relation to their masses. Also, some confusion on this issue is due to the fact that our equipment and methods are still far from perfect, and because of this, errors are often made in the measurement process. For example, the Dragonfly 44 galaxy, which was originally called a galaxy consisting of almost one dark matter, after repeated measurements, it was determined that its mass is 6 times less than that given by previous measurements, and the amount of dark matter in this galaxy immediately returned to normal. And the distance to the ultra-diffused galaxy, which was mentioned earlier, varies from 13 megaparsecs to 22 megaparsecs for different groups of researchers, what makes a difference in 1.7 times. And according to the luminosity of this galaxy, according to the inverse square law, the mass estimates differ by 2.8 times. But we must also take into account the fact that astronomers use the luminosity of galaxies to determine the baryonic mass, and the total mass or virial mass is found from the dynamics of objects. And after comparing these masses, they make a conclusion about the content of dark matter in the studied galaxy. The accuracy of estimating the mass from the luminosity depends quadratically on the accuracy of determining the distance. And the value of the virial mass, as we found out earlier, gives an error towards overestimation. And the final result about the content of dark matter depends on two variables, the accuracy of which is not certain. And accordingly, the accuracy of the final result is even less. The existence of dark matter is also indicated by the speed of galaxies in clusters. And in this case, due to the movement of space, towards the center of the cluster, where a strong inertial trap effect takes place. And also, due to the movement of space, there is a double Doppler effect. Therefore, when we see a shift in the spectrum in a galaxy cluster, we see a shift which is due to the movement of galaxy and due to the movement of space. This effect requires further explanation, so it will be discussed in other video. In favor of the existence of dark matter, indirectly indicates the presence of hot gas in galaxies, which is formed as a result of various processes, and due to the gravity of a massive dark halo, remains within the galaxy. But hot gas is also presented in intergalactic environment of galaxy clusters. And because of the gravity of dark matter of the entire cluster, it's kept in cluster. But the appearance of hot gas in galaxies is explained by various processes inside galaxies. Then the presence of a huge amount of hot gas in the intergalactic environment of clusters is not so easy to explain. Where is it from, when it should stay in the galaxies? At the same time, we are well aware of the existence of quasars, blazars, Seyfert galaxies, radio galaxies, and we even know that there are sources of synchrotron radiation in the core of our galaxy, which is emitted when matter moves at speed near to speed of light. There is also a phenomenon in our galaxy that called Fermi Bubbles, which still has no explanation. That is, we know very well that the cores of most galaxies are sources of very high energy particles. And maybe the hot gas is not kept in galaxies, but leaves them and enters the intergalactic environment of clusters. Maybe it also leaves the clusters of galaxies without any difficulty. But it doesn't get smaller, because there's always influx of new gas from the cores of galaxies. There is one more, in quotation marks, proof of existence of dark matter, and I already talked about it in the previous video about dark matter. But here I want to express one more thought. The fact is that Abel 520 is not the only image that doesn't find an explanation in the dark matter hypothesis. There are also many other unexplained images. But the main question is different. Since when can a technique that has not proved to be a reliable tool for research can be considered evidence? When this research technique, together with the dark matter hypothesis, explains all the unclear points of this issue, only then can the image of the bullet cluster be considered evidence. Indirect evidence of the presence of dark matter in clusters of galaxies is the excessive deflection of a ray of light by the gravity of this cluster. There is no doubt that gravity deflects a ray of light, but there is another question. How many experiments have been carried out to test this phenomenon? But it's not about the number of the experiments on the deflection of ray of light, but about the number of these bodies with a known mass for which experiments were carried out. It's not possible to test the entire dependency without experimenting with different values. And can we be sure that we correctly calculate the angle by which the ray should deviate with masses in the trillions of the masses of the Sun? For many years, scientists have been unsuccessfully trying to detect dark matter particles. And every year, the accuracy of installations and experiments is growing. But there are still no results, what prompts many scientists to look more closely at alternative hypotheses. Of course, it can be argued, for example, that dark matter manifests itself in the existence of galaxies with a very thin disk, where the gravitational stability of thin disk is provided by a dark halo, or that without dark matter, galaxies would not have had enough time to form during the existence of the universe. But this and many other arguments are just circumstantial arguments, which are valid only in the existing theoretical paradigm. In general, it must be admitted that the invention of dark matter halo, to some extent, makes life easier for scientists. because almost any anomaly can be explained by some exotic form of dark matter halo. And mathematically it's not hard to prove, but very hard to disprove. And false picture is laid in the mass consciousness, because the information about dark matter coming from the pop science and media is presented very one-sidedly, as if the dark matter hypothesis perfectly explains all the observations, that its application doesn't cause any controversy, that the hypothesis of dark matter has long been proved and generally accepted in the scientific world. But if this were so, then probably so many scientific works would not have been devoted to the topic of dark matter, in which for several decades now scientists have been analyzing the rotation curves and distribution of visible matter, and then trying to pull the theoretical profiles of distribution of dark matter onto the studied galaxies, and get full agreement fluctuating between models of minimum and maximum disks.